Hello, we are Team 8 presenting our final project for the Foundation Engineering course. Our topic today is the Winkler Foundation Model. This project was prepared by Lee Mo-yeon, Chang Jun-hyuk, Jeon Hae-na from Civil Engineering and Jung Jun-hee from Architecture Engineering. I'm Jeon Hae-na and I will start by introducing our presentation. Today we will walk you through the theoretical background of the Winkler model, numerical analysis methods, implementation algorithms, and results interpretation. This presentation consists of four main parts. First, the introduction explains the background and motivation for choosing the Winkler Foundation model. Second, the background theory outlines the theoretical framework of the model, including the finite differences methods (FDM) and exact solution approaches. Third, in algorithmic codes, we explain the computational process and the implementation of the numerical methods. Lastly, the research section compares the outcomes from both methods and discusses the insight gained. Let me now explain the introduction section in detail. This slide provides an overview of the structure and analysis condition addressed in our project. The diagram on the left shows the target structure, which is a foundation under non-uniform loading. Two concentrated loads are applied, each including a dead load and a live load. We applied the Winkler Foundation model to analyze this structure and implemented two user-defined elements. First, the user can set the number of springs. Second, the user can fully adjust the location of the loads. Under this condition, we derived three main structure responses: deflection, bending moment, and shear force. Based on this result, the following slide will explain each analysis methods and algorithm in detail. The background theory section will be presented by Jung Jun-hee.
This slide explains the theoretical background of the Winkler Foundation model. Starting with the basic assumption, the Winkler model idealizes the soil not as a continuous medium, but as a series of independent linear springs. In other words, the soil beneath the structure is assumed to provide resistance through individual springs at each point. Using this idealized model, we can derive deflection, bending moment, and shear force based on mathematical equations. These analyses are performed using two approaches. The first is the finite difference method, which divides the structure into discrete parts and uses difference equations. The second is the exact solution, which directly applies its analytical formulas under given conditions. In our project, we implemented and compared both methods. This slide introduces the finite difference method, or FDM. As shown in the diagram, the structure is divided into equal intervals, and springs are assumed at each node. In this example, two concentrated loads are applied, and the structure is divided into 11 nodes in total. The analysis checks how the loads are transmitted at each node. The procedure is as follows. First, the structure is modeled with two concentrated loads applied. Second, the reaction forces at each node are calculated based on the load distribution. Third, the diffraction at each node is computed using the moment equation and the finite difference method. A central difference formula is used to solve the equation. This method is suitable for modeling complex conditions or varied loading cases due to its numerical and segmented approach. This slide shows the structural analysis process using the finite differences method. The equations in the top left describe the deflection curve of the structure. The bending moment is given as EIY2' is equal to m, and the shear force is EIY3 prime is equal to V. These equations are converted into finite difference forms as shown below. On the right side, the reaction force R sub I at each node is calculated using the diffraction value I sub I. Using these reaction forces and difference equations, we can perform back substitution to predict the overall structural behavior. Now, we explain the exact solution method. The diagram shows a beam subject to a single concentrated load P. The beam is fixed at both ends, labeled A and C, with the load applied at the point B. The position of the load is defined by distance from the left and B from the right, with total length L is equal to A plus B. A key concept of this method is that the coordinate X is defined differently depending on its location relative to the load. If X is smaller than A, the coordinate is measured from point A. If X is larger than A, the coordinate is redefined as X is equal to L minus X and measured from point C. Mathematical features of this method include diffraction and bending moment are continuous at the load point. However, shear force exhibitions discontinuity, its value differ on either side of the load. In addition, both shear force and method moment must be zero at the beam, and x is equal to zero and L to satisfy boundary conditions. The previous slide explained the concept of exact solution, and this slide shows the actual equations used. The equation correspond to the first for diffraction and the second for moment and third for shear force. These formulas are calculated based on the load P, beam length L, load location A, and parameters such as the elastic modulus E, moment of inertia I, and spring constant K sub S. These equations may appear complex due to their combination of hyperbolic and trigonometric functions, but once input values for each location x are given, they can provide highly accurate results. As shown in the bottom right, these equations allow us to calculate y, m, and v with high precision. However, due to the complexity of these functions, we carefully ensured numerical stability during code implementation. Algorithm and code section will be presented by Chung-Ang.
Hello everyone, my name is Jung-Hyuk and let me introduce about our algorithm and codes. This slide outlines the full analysis algorithm based on the finite difference method. The analysis begins with setting the input data. This includes the number of segments, road location, and spring constants. Based on this data, a database is built, and a matrix representing n plus 1 equation is constructed. As a result, we first obtain the deflection value, and using this, two metrics are constructed for further analysis. One is matrix CC for calculating the moments, and the other is matrix DD for calculating shear force, which uses a higher order difference expression like this. Through this process, we obtain the moment, shear, and deflection of the structure. The final results are visualized as numeric tables and graphs. Helping to understand the analysis, this algorithm is also flexible for interactive structure analysis. The code is as follows. This slide shows the algorithm of the exact solution method. Unlike FDM, this method calculates deflection and internal forces by directly plugged input values into predefined formulas. The process starts by setting the input data, including the number of segments, road locations, and spring constants. A database is then built, and the data is applied to the formula. Deflection is calculated, and the result from two sections are summed and multiplied by a factor of 1.515. Shear and moment are also calculated using respective formulas, and their section values are summed and multiplied by 1.515. A key assumption is that the coordinates x is defined based on the load position. If x is larger than a, then x is recalculated as x equals to L minus x from the right end. If x is smaller than a, the original x is used. Through this calculation process, we derive values for deflection, shear, and moments, and present the final result in numerical table and graphs. Although the method requires complex computations, it offers high accuracy. The code is as follows.
The final section result will be presented by Im Uihan. This slide compares the results from the exact solution and FDM. The left side shows the exact solution results, and the right side shows the FDM results. Both were performed under the same conditions with key input values including total beam length L equals 19, elastic modulus E equals 3000 ksi, width B equals 7.848 inch, spring constant Ks equals 153, loads P1 equals 230, P2 equals 290, load positions 6.5 inch and 198.5 inch. Deflection, shear force, and moment values were calculated for the entire beam. In terms of deflection, FDM showed slightly smaller values overall, likely due to its conservative approximation nature. Shear and moment values for both methods showed significant changes near the load points, especially for shear. Sharp sign changes were observed just after the load point. For both methods, shear forces approached zero at the beam ends, and moments also satisfied the boundary condition by converging to zero at both ends. In conclusion, both analyses yielded similar overall trends. FDM is suitable for interactive numerical simulations, while the exact solution is effective under fixed loads and well-defined boundary conditions. This slide visually compares the results from the exact solution and FDM. The left graphs show the exact method, and the right graph shows the FDM results covering deflection, shear, and moment. The deflection graphs show that both methods have minimum values near the center and near zero value at both ends. However, FDM trends to slightly underestimate values. The shear graphs show that the exact method has a sharp discontinuity at the load point, consistent with the theory, while FDM approximates it more gradually. Moment graphs from both methods display a curved shape with maximum negative values near the center and values converging to 0 at the end. Overall, both methods accurately represent structural behavior, with the exact method focusing on theoretical precision and FDM on numerical practically. This slide shows additional graph results generated under different conditions or parameter settings. From top to bottom, the graphs represent deflection, shear, and moment. Compared to earlier results, the values here are significantly larger. Maximum deflection reaches approximately 0.1 feet. Shear up to 2000 kIPS. Moment up to 10,000 kIPS. These large values may result from high input loads, large spring constants, or lack of unit conversion. These graphs were generated not for direct comparison, but to test model functionality and the sensitivity to input changes. These results verifies that our algorithm operates correctly under various scenarios. Thank you for listening to our presentation.